Now we're in same house as parent V4, so we're in the fourth part of getting to work list accumulators. So I'm going to go down here to this problem, design a function that consumes a wizard and produces the number of wizards in that tree, including the root. And your function should be tail recursive. So at first I can go fairly quickly. Let's see, this function is going to consume a wizard, and it's going to produce the number of wizards, so that's a natural. And we'll say produces the total number of wizards in the tree, including the root. That's great for a purpose. Let's see, we should have a check expect for a very simple case, like if we count a wizard that has no children, that would produce 1. And if we count our whole example tree from before, that happens to be 11. And we'll do a stub quickly. That's 0. That tells us that those examples are well formed. And let's see, how are we going to template? Well, we're going to template from the mutual recursion template for wizard. That's this template right here. We'll template from wizard, but we're also going to add an accumulator because we know we need to make a tail recursive. Now, preview, it's going to end up taking 2 accumulators. But for now, we just think it's going to take 1 because we know we need to make a tail recursive. So let me go through and add that accumulator. ACC is, and there'll be some type, and there'll be some invariant. And oftentimes when you use an accumulator to achieve tail recursion, that accumulator kind of ends up being the result so far. We're not sure that's what it's going to be in this case, but let's imagine that that is what it's going to be. So let's, instead of calling it ACC, we'll call it RSF. Okay, so now let's start adding it in here. RSF goes there, and there it's 2 mutually recursive functions, so we have to add the accumulator to both of them. That means when we call fun4wiz the first time, something's got to go there. Let's see, RSF is now an accumulator parameter to this function, so we'll put it there. And this mutually recursive call has to pass a second argument now, which might have something to do with RSF. We'll have RSF here. We'll have RSF here. And both of these mutually recursive calls have to pass an extra parameter, which might have something to do with RSF. And at this point, I've kind of set myself up. I've got my template. So now let's look at the picture of the tree and think a bit more about what this accumulator is going to be. If it's a result so far accumulator, then the eventual result of this function is a natural. So maybe this accumulator is going to have type natural. And if it's a result so far accumulator, then at each point in the recursion, it's the result so far. In some sense, it ought to be something like the number of wizards seen so far. Something like that. So for example, and here's a place where it's a little hard to say how to write the examples. We could write the examples here in the code. We could say, let's see, if we call this thing from the top, count of WK, then the first inner call is fun4wiz on WK. And what would be the count of wizards that we've seen by the time we get to WK? We're not at WK yet. What's the count just as we get to WK? Well, that would be 0. We haven't seen any of them. But then in a second, when we call fun4wiz on WK's first child, which is WH, well, what's the count then? Well, by then the count is 1, because we've seen WK. And so on. You could do them like this. Or what you might want to do in a case like this is not write the examples out in the code, but write them out in a picture. And if we wrote them out in a picture, if we wrote those three examples out in a picture, then we'd have the original picture, and we kind of have 0, 1, and 2 as the accumulator values. And I'm kind of drawing them just above the nodes here to reflect that they're the value kind of just as we're getting to that node. All right, let's try to make that work. Now, we're trying to achieve tail recursion, and here's a mutually recursive call that isn't in a tail position because it has all this stuff wrapped around it. So somehow we got to get all of this stuff out of here, as well as that last paren there, because we need the mutually recursive call to be in tail position. The key thing about tail recursion in mutually recursive functions is that every single mutually recursive call has to be in tail position. So somehow we've got to achieve something like that. Well, let's think about it for a second. If when we get to fun for whiz, just as we get to fun for whiz, RSF is the number of wizards that we've seen so far, then what should the new value of RSF be when we go off to visit the children? Fun for LOW is going to go visit the children, right? Well, it would just be add 1 of RSF, because we got one more wizard, the wizard we're just at right now. And here, that would be 0. Before we go to the first wizard, or just as we're going to the first wizard, our picture tells us that that would be 0. Now, going through the list doesn't change the count. We're going to change the count of wizards that we've seen when in the fun for whiz function. Very often when you have an accumulator in mutual recursion, it'll be one of the mutually recursive functions that changes that accumulator, not all of them. And that's what's happening here. We don't want to change the accumulator value just because we're going through the list. We're going to wait to change the accumulator value when we actually get to a wizard. So this would just be RSF. And similarly, this would just be RSF. Now, what I'm going to do here is I'm going to be a little sloppy for a second, and I'm just going to say to myself, well, let's see. This produces a count, and this produces a count, so I'll combine them together with plus. Now, if you've really absorbed what tail position is and what tail recursion is, you should cringe here, because those two calls are not in tail position anymore. But let's just ignore that for a second. And then when you get to the very end, well, we'll produce that. And here's a question for you. Before I press run here, are any of these tests going to pass? And if they don't, what will the value that gets computed be? So think about that for a second. What will the value produced by this first call to count and this second call to count be? Okay, let's see. So when I run it, the first test passed, so count WA produced 1, but count WK produced 30. Okay, I'm going to leave the question of how 30 popped out of there until a little bit later. The real thing we're going to work on now is, this isn't really tail recursive, is it? These two mutually recursive calls are not in tail position. We got to get them in tail position. And that's what we're going to do in the next video.